Welcome to the Explainer. You know, graphing rational functions, it can feel like you're a detective trying to solve a really tough case, full of hidden clues and weird behaviors. But what if you had a detective's guide? Well, today we're putting on our detective hats to crack the code and uncover all the secrets hiding in these graphs.
So here's our game plan for this investigation. We'll start with the basic blueprint, then see how the evidence can shift. We'll solve the very curious case of the missing point, crack the code for those tricky asymptotes, and finally, we'll put together your official detective's toolkit.
All right, let's jump right in. Look, every great investigation starts with one key piece of evidence, right? The thing that everything else is built on.
And here it is. This is the one, the parent function, y equals 1 over x. Think of this as, the original fingerprint in every single case. See how it's in two separate pieces and they curve away from the center? Well, those curves are defined by these invisible boundaries that they get super close to, but they never actually touch them.
Okay, so that first boundary, that's what we call the vertical asymptote. It's like this invisible wall, a vertical line the graph just can't cross. For our blueprint function, the denominator is just x. So what makes that denominator 0? Simple, right? When x is 0. And that's exactly why the y-axis itself acts as our vertical asymptote here.
And the other boundary is the horizontal asymptote. This one tells us what the graph is up to in the long run, as x gets crazy big in either the positive or negative direction. For our y equals 1 over x, you can see the graph just kind of levels out and gets closer and closer to the x-axis, which is just y equals 0. It gets close, but it never quite gets there.
All right, so let's see how our suspect tries to disguise the evidence. Because let's be real, these graphs don't always stay put. A few simple changes to the function can shift the whole blueprint, completely changing its location.
And this formula, this is where you find the secret code. Those h and k values, those are your biggest clues. H tells you about the horizontal shift, did it move left or right, and k clues you in on the vertical shift, up or down.
And boom, here's what that looks like. The whole scene has been moved. The vertical asymptote isn't at x equals 0 anymore. It's been shifted to x equals h. And the horizontal one? Not at y equals 0 either. Now it's up at y equals k. The shape is identical, but the location? Totally different. Okay, now for a real plot twist. This is a classic, the kind of thing that trips up even seasoned detectives. I'm talking about the case of the disappearing evidence, or what we call a hole in the graph.
So picture this. You're investigating your function. You factor the top and the bottom, and you see it, a common factor. And your first instinct is just to cancel it out, right? Simplify things. But listen, in our line of work, evidence never just disappears without leaving some kind of trace.
And it leaves behind this crucial piece of evidence. The source material calls it a P.O.D, a point of discontinuity. And on the graph, well, it's literally just a hole, a tiny single point that's just gone. The line goes right up to it, skips over it, and keeps on going. So here's the key takeaway, the thing you absolutely have to remember. What's the difference between a factor that makes a vertical wall versus one that just pokes a little hole? It's all about when you find the 0. If a factor in the denominator makes a 0 after you've simplified everything, that's a vertical asymptote. But if that factor gets canceled out on the process, well, that creates a hole at whatever x value would have made it 0. Okay, so we've dealt with shifts, we've dealt with mysterious holes. Now it's time to break out the advanced tools for finding those horizontal asymptotes, especially in the more complex cases. The cool thing is, the rules are actually pretty simple once you know them.
Okay, this slide right here, this is basically your secret decoder ring for horizontal asymptotes. It all boils down to comparing the highest power, the degree of the top and the bottom. Case 1, if the bottom's degree is bigger, the horizontal asymptote is always at y equals 0. Easy. Case 2, if the degrees are the same, you just take the ratio of the main coefficients. Just like in that example from our source material where it was y equals 3 over 4. And case 3, what if the top degree is bigger? Well, that's a whole different story.
Right, so in that special case where the top's degree is exactly 1 higher than the bottom, the graph doesn't level off flat. Instead, like this note from our source file says, it starts to follow a slanted line. We call that an oblique asymptote. And the tool we use to find its exact equation? You guessed it, good old-fashioned long division. And hey, one last heads up from the field. Don't ever assume there's just one vertical asymptote. If your denominator has a bunch of different factors that don't cancel out, you're going to have multiple vertical asymptotes.
Each one acts like its own separate boundary that the graph has to deal with.
So we've gathered the clues, we've learned the advanced techniques, we've gone over the case files. It is time to put it all together. Let's assemble your official detective's toolkit. Just follow these 4 steps in this precise order, and I promise you, no rational function can hide its secrets. Step 1. Factor everything. See what you're really dealing with. Step 2. Find your holes by canceling out any common factors. Step 3. Find your vertical asymptotes from whatever's left in the denominator. And finally, Step 4. Use those degree comparison rules we just talked about to nail down your horizontal or oblique asymptote. That's it.
And just like that, the case is cracked. What might have looked like a totally confusing mess of curves and lines before is now a predictable pattern, and it's all governed by a very clear set of rules. You now have the complete toolkit. You know the procedure. So, the only question left is, which function are you going to investigate next?